Okay, good morning, everyone. I just wanted to review the end of the last lecture quickly. So we were talking about preconditions and postconditions of methods. Everything that I was talking about also applies to constructors. So the preconditions and postconditions essentially describe the contract between the caller of the method and the method itself, right? So the preconditions and postconditions explain what the method, well, they formally describe what the method is supposed to do, right? So by formally, I mean it's supposed to be mathematically describes what the method does. Okay, so the postconditions, that's a condition that must be true when the method finishes running, right? So immediately after the method finishes running, there's some condition that has to be true. Right? Now the responsibility for meeting the postcondition lies with the method, right? So the method is responsible for ensuring that whatever condition, whatever postconditions it has, that they must be true, right? And if the postconditions are not true, then there's something wrong with the way, with your implementation. Okay, so now for a non-static method, postconditions can involve lots of things, right? So if the method returns a value, right, the method might promise something about the returned value, right? So whatever it promises about the returned value, those things must be true, right? If a method belonging to a class, belonging to an object changes the state of the object, then there's a condition on one or more of the fields of the object. And finally, if a method has an argument or has a parameter that's a reference type, then there might be a condition on the state of that of the object that's passed in after the method finishes running. Right? So in Java, you can't actually write, there's no sensible way to write a formal postcondition. Right? So there's no mechanism in the language that actually lets you check whether a postcondition is true. Right? You can sort of hack your way around it, but it doesn't actually work. Okay, so here's an accessor method for the point2 class. Right? All it does is return the x coordinate of the point. Right? That's all it promises to do. Right? And you might ask yourself, so what's the postcondition of this method? Well, the x coordinate of the point. The method should return the x coordinate of the point. Right? But it's actually more involved than that. Right? There's actually more involved to it. So the actual postcondition is that the x coordinate of the point doesn't change when the method is called, right? And the y coordinate of the point doesn't change when the method's called, right? And the actual x coordinate is returned by the method, right? So it's actually quite hard to write these, right? So it's awkward to express these in Java, right? So to check that the x coordinate and the y coordinate don't actually change, right, I need to record what is the x and y coordinate when the method first starts running, right? So these two lines up here, they have to be the first thing that happens when the method runs, right? So remember what the original x and y coordinates of the point are, right? And then get the result, which is just the current x coordinate, right? And return the result. Now, what you really want to do for the postcondition is immediately before you return or immediately after you return, right, you want to check that postcondition. But there's no way to check the postcondition in Java after the method returns, right? Because the return statement always ends a method. So there's no mechanism in Java that lets you do this the correct way, right? But the postcondition, should you choose to check it, would be something like this x equals old x, right? So the x coordinate doesn't change, right? And this y equals old y, the y coordinate doesn't change. Right? And this x is equal to the result, right? So the result is actually, equal to the x coordinate of the point. Right? That's just an accessor method that just returns a field, right? You've got to do all this stuff, right? And Java was never designed to support this. This is part of design by this is part of a software engineering technique called design by contract, right? Where you specify the contracts of the methods by saying what the preconditions are and what the postconditions are. Right? When you say what the pre and post conditions are, they're expressed as conditions, right? So something that's actually true or false, right? And the reason you do this is because you can actually check, right? And there are languages that actually check whether preconditions are true before methods run, and there are and they will check, are the post conditions true after the method finishes running. Okay, so that's just an accessor method. So you can imagine that a method that changes the state of the object is even more complicated to write its postconditions, and that's true, Right? So the postconditions for a mutator method, right? So that's a method that changes the state of an object, right? That typically involves the fields of the object, right? So if I change the x coordinate of a point, right, then I'm going to actually, right, so this method here changes the x coordinate of a point, so it actually has to set this dot x, right? And so what does the postcondition here look like? Well, it's, again, awkward to write, right? And these methods are really simple, right? They're really simple methods, but to actually formally write their postconditions is very complicated. Let me back up here. So what should set x actually do? Right? So it should change the x coordinate to the specified x coordinate, right? And it shouldn't change the y coordinate. Right? So there's a couple of things that you have to check here. Right? Okay. So the very first thing I have to do is I have to make a copy of that x coordinate that comes in. Right? So I'm making a copy of new x, and I'll explain why in a minute. Right? I'm also making a copy of this dot y, and that's for the same reason as for the other method. Right? Because I want to compare that the y coordinate I want to check that the y coordinate doesn't change. Right? Then I have then I actually have the line of code that changes the x coordinate. Right? So this x equals new x. Right? The result is going to be, I'm just going to return a reference to this point, right? So I need that. Right? So there's actually two things that we're checking here, right? Because this method returns a value and it modifies a field, right? And then I return the result, right? Again, I want to check the postcondition after I return the result, but I can't. If you could, that would be the postcondition, right? So the new x coordinate of the point equals, now it's param x here, right? So it's not new x here, it's param x, right? It's the copy of the passed in x coordinate, right? I want to check that the y coordinate didn't change, right? And I want to check that the result matches what it's supposed to be, right? So in other words, I want to check that it actually returned a reference to this point. Okay? Now, why did I have to make a copy of that parameter there? Right? It's because there's nothing from stopping you from doing something like this. Right? So you can change the value of a parameter inside of a method. Right? So inside the method, I can write new x equals 1, which is wrong. Right? It's wrong unless new x is equal to 1. Right? But it's probably going to be wrong. Right? And then you can go ahead and assign this x equals new x. Right? And now your method's broken. Right? So the reason you're making a copy up here is to protect against any weirdness that's going on inside the method. Right? This is a very simple method, so you can just look at it and say, oh yeah, that's fine. Right? If that line is there, you would say, hey, what's that line doing there? That can't be right. Right? But if you were trying to formally prove that this method was correct, right, you need to make that copy up there to guard against weirdness like this. Right? So if you check this postcondition with this method, you'll see that this x equals param x is no longer true. Right? Unless param x happens to be 1. Right? Right? So that's why you're making the copy of the field up there. Right? Sorry, that's why you're making a copy of the parameter at the beginning of the method. Okay, so is there actually any way to check a postcondition? Right? So you can try. Right? You really want to do it after the return statement. So immediately you can conclude that Java can't do this. Right? But you might be willing to compromise and say, well, okay, I'll check it right before the return condition. Right? So how do you check it? Well, you could use an if statement. Right? So inside every method, you can have an if statement at the end of the method that checks whatever postconditions should be true. That checks the postconditions, sorry. Right? Inside the if statement, if the postcondition is not true, you can throw an exception. Right? Which is fine. The problem with doing that is anytime someone calls one of your methods, right, the method has to check its postconditions. Right? That takes some time. It might be fast, but it still takes some time. Right? So that imposes a cost on every caller of the method. Right? Whoever calls your method's got to pay for the price of checking the postconditions. Some languages, actually, you have to pay this price. Right? So that's an example of what it would look like. Right? You just put the postcondition in as an if statement and check if it's true. In this case, I'm checking if it's false. Right? So there's your postcondition, and then you negate the whole thing. Right? So in other words, if the postcondition is false, throw an exception, and away you go. Right? So you could definitely do that if you wanted to. Right? Now, usually, you're checking preconditions and you're checking postconditions while you're developing your code, right? You're not normally checking postconditions when the code is, when you ship the code to run, right? Not normally anyway, right? So normally this is a tool to help you when you're developing your code, right? So instead of using an if statement, you can use what's called an assert statement in Java, right? So an assert statement, it's just the word assert, and then there's a condition, right? If the condition is false, then assert will cause an error to occur, right? Now, the difference between, now that sounds exactly the same as doing this, right? But there's a difference, right? So the difference is you can turn assertions on and off when you compile your program, right? So you turn them on when you're developing your code and testing your program, right? And then you turn them off when you're confident that your program is error-free, right? So in other words, you turn them off when you ship your code to the customer, right? So now it just looks like that, right? So you just replace the if statement with an assert statement, right? And you let assert deal with whether or not an exception is thrown, right? And so it just looks like that. Now, if you compile your code with assertions turned off, that line never runs. So whoever's calling the method doesn't pay the price of checking the condition, right? Here, the condition's really cheap to check, right? But you can imagine a very complicated object having an extremely complicated postcondition, right? So for example, if this method was supposed to sort a list, right? Now you have to iterate over the list and check that it's sorted. You have to do a bunch of other stuff too, but at a minimum, you have to iterate over the list and check that the list is sorted, right? If you have a huge list, that takes a lot of time, right? Well, that takes a lot of time that you don't normally want to pay for. Okay, so assertions are turned off by default in Eclipse. So if you wrote this, if I wrote this in your Eclipse program and you ran it, even when you know the postcondition is false, nothing would happen. Right, so you have to turn them on if you want to use them, right? That describes how you turn them on, right? So you just follow the steps and you can turn them on if you want to. Right? Similarly, you follow the same steps, but you turn them off, right? So you remove, in step 4, you remove the flag -EA. Right? Okay, so that's all I want to say for the time being for preconditions and postconditions. I guess what else do I want to say about it? So this seems really formal, what I'm talking about. It seems unnecessarily formal, right? For a method like this, do I really want to add these 2 lines of code? Do I really want to add these lines of code? Probably not, right? Probably not. And that's why I mean, like 99.9999% of Java programmers don't do this, right? But what thinking about the pre and post conditions forces you to do is it actually forces you to think about how to implement your method, right? And it forces you to check whether your method is doing what it's supposed to do, right? Okay. If you were in the lab this week, then you would have heard this discussion about class invariants, right? So an invariant is just a condition that should always be true, right? So a class invariant is a condition regarding the state of the object that should always be true, right? The invariant, right, should be established when the object is created, right? So if you got an object that has an invariant, right, then the constructor has to make sure that the invariant is true when the constructor finishes running, right? If you have any methods, well, any public methods in the class, right, the public methods have to ensure that the invariants are true after the method finishes running, right? Now, a lot of classes have no interesting invariants, right? So point 2 doesn't have any interesting invariants on its fields, right? It has an x coordinate, it's got a y coordinate, and that's it. There's no restrictions on what x and y can be, right? So there's nothing. So point 2 is not a good class to talk about regarding class invariants. But the counter class does have an important invariant, right? So in the counter class, it's got this field called value, and the value is always supposed to be 0 or greater, right? Now you know ints have a maximum value, so the value also has to be less than or equal to the maximum value of an int, right? So in your counter class, that's your invariant, right? That's the thing that you want to make sure is always true, Right? Now, if you actually go and look at the implementation of the counter class that I showed you, right, and you look at all the constructors and you look at all the public methods, you can convince yourself that, in fact, that is the case, right, that this thing here is always true. Right? As soon as that's not true, your objects no longer behave the way they're supposed to behave. Right? So a class invariant has to be true at the end of every constructor and at the end of every public method. If you have a private method, so a method that no one else can call, the invariant doesn't necessarily have to be true after the private method runs, right? But if you have a private method, you're calling it from somewhere else, right? So you're probably calling it from a public method somewhere. And so the public method, when it finishes running, it has to ensure that the invariants are true, right? Again, you can check your invariants using assert, right? So here's your counter class, right? Now, I don't want to manually write this in every time, right? So I'm just going to make a method that does that for me. Right? So I've got this private method called checkInvariant that simply asserts that the value of the counter is always greater than or equal to 0. Right? I don't have to check the other part of the assertion. Right? I don't have to check that the value is less than or equal to integer max value. Right? Why don't I have to check that? Because the field's an int. Right? That field there is an int, so I know it can't possibly be greater than integer max value. Right? Which is why the invariant's written like that. Okay, so every constructor has to ensure that the invariants are true. Right? So at the end of the constructor, you just call your checkInvariant method. Right? I have another constructor. Right? So when the constructor finishes running, the invariant has to be true, so you just check down here. Right? And you can see, right, that this constructor does, in fact, enforce the invariant, right? Because if the value is less than 0, right, if that value that gets passed in is less than 0, an exception is thrown, right? And then immediately after, the field value is assigned that value, the passed-in value, right? So you know that when this constructor runs, right, just by looking at the code, you know that the invariant is true, right? But it wouldn't be true if you didn't have that if statement, right? So if you didn't have that if statement there to check that the passed-in value is in fact valid, right? Then that invariant can fail, or that invariant can be false, right? So that's why that if statement's there. Copy constructor, so it's another constructor, right? So you have to, when that constructor finishes running, the invariant should be true. For value, right? So value just returns the value of a counter, right? Now, again, this is the problem in Java, right? You want to check that the invariant is true after the return statement, but you can't, right? So you're stuck checking it immediately before the return statement, right? So I do want to point out there are languages where you can, in fact, that automatically check the invariant after the return statement. Right? Java just doesn't happen to be one of those languages. Okay, here's advance. Right? Advance is another one of these methods where the invariant might become wrong, where the invariant might become false. Right? But if you read that code and understand what it's doing, right, you can convince yourself that, in fact, the invariant does hold after this method runs. Right? So if the value happens to be equal to integer max value, right, I set it to 0. Right? Instead of adding 1 to it. Right? If I just add 1 to it without that if statement, so if I just write this value plus plus, right, then what happens when the value happens to be integer max value? It wraps around to some negative value. Right? And that causes the invariant to be false. Okay, so the string, now you might think, why am I checking the invariance in a toString method? Right? It's because you can change the fields inside of toString. Right? So inside toString, you could do something silly like call advance, right? Which would cause the, not call advance. You could set the value of the counter to some negative value if you wanted to, right? So you can check the invariant here as well. Again, you want to do it after the return statement, but you can't, right? Okay, so that's how you could, if you wanted to, check all of the invariants for your class. Right? So the next lecture you don't have access to yet. I didn't post it yet because I wasn't sure I'd actually get to it, but I guess I did. Okay, so now we want to talk about static features of a class. Right? So far, when we started talking about creating classes and objects, we've only talked about non-static features. Right? Class has some fields, it's got some methods. Right? None of the fields and methods so far have been static. Right? But before we started talking about classes and objects, everything was static. So what's the difference? Right? Okay, so a class can have fields and methods that are static. Right? So you already know that you can put static methods into a class. Right? But I'm telling you now, you can also put static fields into a class. Right? Now the difference between a static feature and a non-static feature is that the static stuff belongs to the class. Right? It does not belong to any individual object. Right? So it belongs to the class. Okay, if you have a field that's static, right, we say that it's a per class member. All that means is it belongs to the class. Right? And so when I say it belongs to the class, what I really mean is that there's only one copy of the field. Right? And the field is associated with the class instead of it being associated with an object. Right? So in the point 2 class, you know that every object has an x and y coordinate, right? Those fields are non-static, so every object gets its own x and y coordinate. If you have a static field, then no object has that static field, right? The field belongs to the class, right? But the objects can get to that static field, right? So every object created from a class that has a static field, it shares the exact same copy of that field. Okay? So you also see static fields called class variables by some writers. Right? So it's called a class variable because it belongs to the class, not an object. Oops, sorry. Okay, so this is the Domino class. If you've been reading the notebooks, you've seen it already. If you haven't been reading the notebooks, then, well, that's what a domino looks like, right? One of these tiles. So a domino is just it's a piece in a game. Well, in many types of games. Right? It has two sides every domino has two sides, right? And there are all of the dominoes in the, I forget what this is called. This has a name, this set of dominoes, but I forget what it's called. But you can see that the values that a domino can have, right, vary from 0 to 6, right? And each side of the domino has its own separate value, right? So every domino has two values. Okay, so you can implement this class pretty easily, right? It's going to look a lot like the point 2 class, right? Except that your values are ints, right? So here I've got val1 and val2. They're both ints, right? So val1 and val2 just corresponds to the value on side 1 and side 2, right? But I've also got these static fields, right? So I've got a static field called min value. I've got a static field called max value, right? They're public, right? And they're final, right? So they're written in all caps. Because they're public, static, final, they represent constants that are meaningful to the class, right? And it's obvious what they represent, right? It's the minimum value and the maximum value that one side of the domino can have, right? Because they're public, they also have comments, right? So they have java.comments that will appear in the documentation when you java.doc your class, right? Okay, now what does this look like in memory? So it looks like this. Right? Okay, so I make two dominoes. Right? I got the domino 1, 3, and I got the domino 5, 5. Right? So D1 is the object at address 1000. Right? D2 is the object at address 1100. Right? When you use the domino class for the first time in your program, it gets loaded into memory. So there's the domino class. Right? It's incomplete. Right? It should have a field val1 and val2, but that's fine. There's not enough room on the slide. But the important part is that it's got the two static fields here. Right? So min value and max value have the values 0 and 6, and they're stored in the class. Right? Sorry, I keep on forgetting to turn on this thing. Okay, it's stored in the class. right, those two values. Every domino object, right, has its own val1 and val2. Right? So the domino 1, 3 has the values 1 and 3. The domino 5, 5 has the values 5, 5. But what's not here and what's not here are these two values here. Right? So the static fields belong to the class. Right? The objects don't have their own copies. Right? So really what's happening is this is just a way of storing information somewhere else. Right? Instead of storing them in the objects, I'm going to store them in the class. Why am I storing them in the class? Because these values never change. Right? So it doesn't make sense to make every object store them. Right? You could store them in the class, but then every domino takes up 4 chunks of memory instead of taking up 2, right? Which is a waste of memory. Okay, to use a public static field, you should not use an object reference. Right? You use a class name. Right? So it's static. Whenever you use anything that's static, you always use the class name in front of the thing that you're trying to use. Right? So if you want to use min value, you write domino.min value. Right? Java is somewhat lenient in that it is legal, but considered bad form, to use an object reference to access the field, a static field. Right? So this is legal. You can make a domino and then write d.min value. Right? But don't do that. Right? So the reason you don't want to do that is because every other Java programmer is going to look at that and say min value is not a static field, right? Because you're accessing it through an object reference. Right? Whereas any Java programmer that reads that immediately knows that min value is a static field. Okay? If a field is marked final, I've talked about this already, it can be only assigned to once. Right? So a public static final field, you typically give it a value when you declare it. Right? So it's very common to see public static final int min value equals 0. Right? So it's very common to see the equals something on the right-hand side here, right, at the point of declaration. If you want to, you can leave it off and then set the value of the field inside the constructor, right? But that's not normally done, right? So a constructor initializes objects, right? This thing here belongs to the class, so the only sensible place to put the initialization is inside the class itself, right? And not in a constructor. If you have a public static final field, you're telling everybody in the world that this thing is a constant, right? That's what you're trying to tell everybody. That's what the meaning of a public static final field is. Right? It's supposed to be constant, and it's supposed to be meaningful to the class. Right? So here I've said it's a meaningful part of the abstraction provided by the class. All that says is min value and max value make sense for a domino. Right? That's all it's trying to say. Okay, so if you have a primitive static final field, right, then it really is constant. Right? So here I've got public static final int, so its type is int, and I've assigned it a value. Right? I can't give it another value because it's final. So this is really fine. This really is a constant. Right? If I try to write domino.min value equals something else, right, the compiler won't even compile the program. Right? So this error will be caught at compile time. Right? And the compiler will complain that min value is final and already assigned to. So if you have a primitive public static final field, it really is constant. If you have a final field that's also whose type is immutable, it's also constant. Right? So string is an immutable class. Right? So in other words, string objects, you can't change them once you make them. Right? That's what immutable means. Right? You cannot change the state of an object after it's created. So if I make the string capital X, if I make the string peekaboo and store it in a final field called x, right, then you can't write code like this. Right? So you can't write nothing to hide .x equals some other string because the compiler won't let you. Right? The compiler will complain that the string x is marked final and already has a value. Right? So if you're using immutable types, everything's fine. Right? So in other words, you can still do this and there's no problems. Right? Okay. If you have a final field of immutable type, then it can't possibly be a constant. right? Because its state can be changed. So here, I've written public static final list of string called empty is a new array list, right? So at that point in time, that list really is empty, right? Because that constructor makes an empty list, right? Presumably, it's called empty because it's always supposed to be empty, right? The problem is you can write code that looks like this, right? So I can use that field empty, right, by using the class name in front of it because it's public, right? And then I can call a method on it. So I can call add, for example, right? And I can add the string oops to the list, right? And it works, right? This will work, which is not good because now empty is not empty anymore, right? Which is deceiving at best, right? So it's deceiving or misleading at best. Okay? So if you make a public static final field, right, you're trying to tell everybody that thing is a constant, right? If you do that, the type you use here can't be mutable, right? In other words, it can't have a method that changes its state. Right? So you should avoid using mutable types as public constants because they are not logically constant. Right? So the weird part in Java is there's no mechanism to force something to be immutable. Right? So there's no mechanism that you can use to mark that list as being constant somehow. Right? There are other languages where you can, in fact, mark that thing as being constant, and then you can't change its state. Java is not one of them. Oh, sorry. Static methods. Okay, static methods are exactly the same as static fields. They belong to the class. They don't belong to any object. Right? So the user of a static method doesn't need to make an object. Right? All they need is the class. Right? And you call the method by using the class name in front. Right? So you already know all of this. Inside the Domino class, there's a method called isValueOK, right? That checks, is this value that you pass in, is that a valid Domino value, right? So is it a number between 0 and 6, right? It's marked static, right? Because you don't need access to the fields of any Domino object, right? Whoever's calling the method is asking, is that value okay, right? They're not asking you, is the value of this Domino okay, right? They're asking you, is this number okay for a Domino, right? Now, because you don't need access to any field, any non-static field of a Domino, you can mark this as being static. Right? Right? So inside the method, there's no this dot or anything like that. Right? There's no dot val1 or dot val2. Right? So this is a good candidate for making a static method. When you call a static method, you always use the class name. Right? So when I use isValOK, it's always domino.isValOK. Again, in Java, it's legal, but considered bad form to call a static method using an object. Right? So you can make a Domino object and call isValueOK using the object. Right? You should avoid doing that. Again, the reason you should avoid doing that is because any other Java programmer who looks at this is going to think isValueOK is a non-static method because you're calling it via an object, right? Instead of calling it through the class name. Eclipse will underline this in orange if you try to do this. Right? So it'll try to warn you that you're calling a static method with an object. OK. So there are utility classes. We've seen utility classes a little bit already. So I've already mentioned them in class. Now remember, a class is a model of a thing or a concept, right? And the normal usage of a class in Java is you use the class to make objects, right? That's almost always the case. Right? Every once in a while, you'll have a class where you don't make objects using the class. Right? So very, very occasionally, you want to make a class called a utility class. And the purpose of that class is not to make objects via constructors. Right? So these classes don't have any constructors, right? Because that's not the purpose of this class. Right? In a utility class, everything is marked as static. Right? Again, because you're not making objects, right? So there's no objects to call methods with. So everything's static, and everything belongs to the class, right? There's not very many of these even in the Java standard library, which is enormous, right? The library is enormous. I don't know if you looked at the number of classes in there, but it's huge, right? There's only a handful of these utility classes, right? Math is one of them, right? Because you don't make a math object, right? You just call these methods that compute mathematical functions with values that you pass in, right? Arrays is a utility class where all the methods operate on arrays. Collections is a utility class where all the static methods operate on some Java collection, right? So the purpose of a utility class is to group together related fields and methods, right? Where creating an object's not necessary, right? So math, you've just got some constants and functions, right? The constants are pi and e, right? You got functions like cosine and sine, right? You don't need a math object to compute any of that stuff, so why make objects, right? Collections, it's just methods that operate on Java collections, right? You don't need an object to sort a list. All you need is the list, right? So it doesn't make sense to make a collections object. Right? So a utility class is never used to make objects using via a constructor, right? It might return objects, so it might make objects, right? But it's not, it doesn't have a constructor, so you're not making objects of the utility class type, right? When you use a utility class, only the class itself takes up any memory, right? So math.cos, math.sine, there's no math objects here, right? So there's no math objects in memory, right? There's just the class. Okay, so if you want to make a utility class, right, for whatever reason, it's pretty easy to do, right? Everything's just static, right? So that's pretty straightforward. It's what you did for assignment 1, right? Here I want to make a utility class that lets someone calculate E equals mc squared. This is Einstein's equation for mass energy equivalence, right? It's only going to have one method in it, right? So m is the mass in kilograms, c is the speed of light, and E is the energy. Right? Okay, so you make your class just like you'd make any other class, right? So there's nothing different there. I've got a final constant here. So I've got a constant here representing the speed of light, right? It's public, static, and final. And it's a primitive type, so I know it really is constant, right? This makes sense to make this a constant because the speed of light is a universal constant as far as we know. And you've got your equation, you've got your method here, right? So it's just public, static, and whatever the return type is, give it a name, give it whatever parameters it needs, right? The energy is just mc squared, so it's just mass times c squared, and then you return the energy, right? So there's nothing really interesting here, right? Everything's static. Everything's static. Right? How do you use the class? Well, everything's static, so I use the class name to call whatever method I want or to access any public fields. Right? So I'm going to call mass energy with a mass of 1 gram. Right? 1 gram. And that spits out this enormous number here. So that's 9 times 10 to the 13 joules. Right? That's roughly the amount of energy released by the first atomic bomb that was dropped on Japan. Right? So if you convert 1 gram of matter into energy, it releases a huge amount of energy. Right? And that's why we have nuclear power plants. Okay. Now, our relativity class, our utility class, doesn't have a constructor. Right? That's all it is. Right? It's got a constant here. It's got a method here. Right? No constructor. But you can write that. Right? So if you write that at this point in time, with our class as it is, that works. Right? So I can, in fact, make a relativity object, which is not the point of a utility class. Right? So why does that happen? So remember, I did tell you that if you don't define any constructors in a class, Java gives you one. Right? It gives you the no argument constructor. Right? So in other words, you get this even though we never wrote it. Right? Okay, so in a utility class, you should prevent this from happening. right? If for no other reason, then you don't want to waste memory with all these relativity objects that we shouldn't have in the first place, right? So how do you prevent the constructor from creating a constructor for, the compiler from creating a constructor for you, right? Oops, sorry. You make your own private constructor, right? So anything that's marked private can't be used outside of the class itself, right? So if you add a private constructor, no one can call the constructor, right? So you just stick in a private constructor. It doesn't matter what the parameters are. You can put whatever you want in there, right? But if I put in a private no argument constructor, right, the compiler won't try to insert one for me, for you, right? Now that it's private, no one else can write new relativity, right? And because a constructor exists, the compiler won't put one in for you. And so now you've stopped anybody from making an object using your utility class, right? So every utility class ought to have one of these private constructors in it. Right. I think that's a good place to stop. Yeah, that's probably a good place to stop. There is a little bit more to this lecture, but I'm going to leave it right there. Okay, so everybody have a good reading week. Take some time off if you can. There will be an announcement on OnQ describing what's covered on the midterm, and there will be a practice midterm or 2 or 3 that will show up shortly. Okay?